We are going to take a look at Imandra's log analysis tool and demonstrate how it can be used to analyze fixed logs and validate them against an IPL model. Here is a model written in IPL. It's quite simple, but also complex enough to allow us to model some interesting trading scenarios. Let's take a brief look at this model, starting from the definition of new order single messages, which are made of several tags like client order ID, order quantity, and so on. In addition to tags, a message declaration also includes validation statements that formally encode the logical conditions under which this type of message should be considered valid and accepted by the system. So, for example, this validation statement here enforces the presence of a positive price tag for limit orders, while this statement here enforces the absence of that same price tag on market orders. Now, in IPL, we model a trading system as a state machine. So here's the definition of the data structure that we are going to be using to model the state of the system. In this model, we process one message at a time. So the state will need to keep track of various details of the particular order being processed at any given moment. Such details include things like the order status and the quantity left to be traded. State changes are triggered by certain events, like an incoming message. Here, for example, we define the system's reaction to an incoming new order single using a receive block. In addition to updates to the state based on the incoming message, we also specify that the system should send out an execution report in response to the submitted order. To model trading behavior, we define a fill action. Actions essentially represent asynchronous events. So with this fill action, we want to represent the event of a previously submitted order successfully matching and trading with a different order from another party. Since IPL models are structured from the point of view of a single party, the fill action here makes no mention of the counterparty's order, but only includes information that we can actually observe from our viewpoint, like the matching price and quantity. To model the system's concrete behavior in response to an action, we use receive blocks, as before. In this case, when a fill action occurs, the system's concrete behavior should be to send out an execution report message informing of the transaction. Once we have defined the entities of our model, we can put them together as message flows, which are sequences of messages and actions that represent the intended trading scenarios for our system. In our example here, we want to model a message flow of a new order single followed by a single fill action representing a trade for the entire quantity of the order. Now, let's say we have a concrete implementation of a trading system and we want to make sure that this IPL model constitutes an accurate specification for that implementation. One way to do this is to use Imandra's log analysis tool to analyze the observable behavior of the real implemented system. What this tool does is, in essence, the following. It takes an IPL model and a sequence of concrete fixed logs produced by the real system and verifies that the fixed logs are coherent with the trading logic specified by the IPL model. We call a single sequence of logically related fixed messages a trace. The analysis performed by the tool is done in multiple steps and at different conceptual levels. For example, not only the tool verifies that all messages in an input trace have the required tags and pass the validation statements, but it also checks whether the whole fixed message sequence fits any of the message flows defined in the IPL model. Let's see the log analysis tool in action on some concrete example of fixed traces. We have here the IPL file of the model we have just seen and a directory with some files corresponding to fixed traces. As we can see, each trace is a sequence of fixed messages produced by the trading system under analysis. This trace here, for example, is a sequence of a new order single followed by two execution reports acknowledging two trades involving that order. We can then use the Imandra command line tool to run the log analysis on the IPL model and the set of traces. The results of the analysis will be saved as a JSON file as shown here. We can then use our trace visualizer to inspect the results of the analysis and thus use these results to assist in debugging any potential issues with the IPL model or the implemented system. To demonstrate this, I've prepared some JSON files, each containing the results of a full log analysis on the model and trace set, at different stages of development of both the IPL model and the implemented system. Let's load the results in the visualizer. At the top here we have a general summary of the analysis outcome for every test run, with a count of the passing traces versus the failing traces, as well as a breakdown of the types of errors affecting each run. This gives a general idea of the development progress and its trend. We can then inspect individual test runs in full detail. After selecting the desired test run, we see here a percentage of correct traces versus incorrect ones, as well as a differential with the previous test run as a rough measure of trend. Down below here we can then select individual traces within the test run and inspect its results in detail. We can filter the list of displayed traces by analysis outcome, which is useful in the case of test runs with a large amount of traces. Let's select a trace from the first test run. As we can see, all of them failed due to a conversion problem from the fix message to the IPL model. We can take a look at the details of the error and see that it was caused by a field, transact time, which was declared to be part of new order single messages in the IPL model, but wasn't found in the actual fixed trace. Let's decide in this case that the fixed trace is correct. The error thus becomes one of overspecification of the IPL model and can be fixed by relaxing the model to not mention transact time fields. We fix the model and run the analysis again. This run now shows 2 passing traces and 2 failing ones. Let's examine this trace, which failed due to a validation error. From the details of the error, we can see that the new order single from the trace did not pass the limit price validation check. This is because its order type is limit, but the message does not include a price tag. This is an error in the real implemented system that produced the fix logs, and therefore must be fixed on the implementation side. Let's take a look at the other failing trace. In this trace, the first 2 messages pass the analysis, and we can see the IPL events corresponding to them. The analysis fails, however, on the last message with index 2, which is a fill execution report. As confirmed here by the description, the analysis failed because the tool could not instantiate a fill action matching the concrete execution report. In other words, this fixed message is not recognized as an execution report that could possibly arise from a valid trade, according to the IPL model. We can examine the message here and observe that the execution report has an order status of equal to 1, which is partially filled, while the traded quantity shows the whole quantity of the original order. We can go back to the definition of the fill action in the IPL model and see that this combination of order status and traded quantity is not acceptable. This is again an error in the real system and must be fixed on the implementation side. Note that the analysis results here don't give any particular hints on what could be the problem with this execution report. The reason being that there are potentially many different ways in which the model or the system could be adjusted to fix the problem, none of them being necessarily any better than the others. In this scenario, for example, the issue could be with the wrong value of the order status field in the execution report, or perhaps the last quantity field indicating the traded quantity, or even a problem with the order quantity indicated in the original new order single. In any case, let's assume we can resolve these 2 issues in a couple of iterations, bringing us to the 4th test run. Now all traces passed the model validations, but there is still one more aspect of the log analysis that we haven't considered yet, which has to do with the message flows included in the model. If a model includes message flows, we can use IPL's region decomposition to analyze the model and compute a map of all the possible state transitions that fit the message flows we have specified. We can then use this decomposition with the log analysis tool, which will then check whether the concrete fixed traces we provided as input match any of these state transition paths. This analysis is very useful to identify modeling issues where some message flows might be missing from the model, as well as to flag potential implementation errors, where the trading behavior observed from the actual system deviates from the intended scenarios. We can separately check if the analysis succeeded in matching the trace with one of the model's state transition paths. In case of a full successful match with a message flow, we can see that each event in the trace corresponding to a state transition shows a corresponding region index. This region index in turn maps to one of the decomposition cases listed in the IPL decomposition job. In case a trace lacks a full match, we can still see which subset of its events matched. As we can see here, the analysis failed to match this trace with a corresponding region decomposition path because the trace contains two fill actions, but in our model here, we have only declared a message flow with a single fill. In this case, the issue is with the model, and we can easily patch it by adding a second message flow, which now expects two fills. If we run the analysis again on this updated model, we can see that now all traces pass the model validations and match with a corresponding message flow.